So after we practice worksheet 2D, let's continue with a few more concepts. The first we want to continue is the axial deformation delta axial, something we defined earlier, axial deformation. So it change in length in the longitudinal axis of a body. And if you have the equation for the normal strain 6 epsilon A equal to delta, that is the axial deformation over L naught. And then we also have an equation for the modulus of elasticity or Young modulus, E equals sigma over epsilon. So let's write down here, we have the epsilon with E the normal strain, it equal to the deformation, let's talk earlier, over the L naught. So from that we can have the deformation in this equal to L naught times the epsilon. And from Young modulus equation, we have E equal to normal stress over normal strain epsilon. From that, we can have epsilon equal to epsilon equal to sigma over E with that transformation. And go back to the lesson number 1, the normal stress. Sigma, what is that? Equal to the load divided by the areas. So P divided by cross-sectional area, P over A. So with that 3 equations, basically, we can find out the deformation, axial deformation delta for a body. So it will be delta, and you can see L naught over epsilon. So epsilon L naught, the first equation here. If I plug epsilon in, so it will be sigma L naught over Young modulus, and sigma equal to P over A. So we can have it P over A E L naught. And that is, or you can write down the deformation, axial deformation equal to P L original length over A, the cross-sectional areas, times the Young modulus. So that is the, basically, if we have the load, we know what material to find out the Young modulus, what is the cross-sectional areas of that, what is the length, you can find out the axial deformation, delta equal to PL over AE. So that the concept, keep that in mind. And moving to the next concept is shear strength. Because you have normal stress, then we have normal strain epsilon, normal stress sigma, normal strain epsilon. Now we already learned shear stress. The associate, it will be shear strength. So let's talk about shear strength. And for shear strength, it call it at gamma. And read at gamma. And in the deformation, we have 2 types of deformation. The change it in length, in the width, in the thickness of the bodies, of the material, that of the structure, that we call it normal strain. The other time of change, the other time of deformation is the angular distortion. And to show you what the difference between those 2 types of deformation, I have a demonstration now, and after that we will go back to get with the equation for shear strength. So as we about to talk the shear strain, we just want to reinforce the stress and strains. As you recall, the stress measure the intensity of the force, and strain to measure the intensity of the deformation. And so far we talking about the normal strain, which is measure the deformation in terms of the changes in length or the width or the thickness. For example, the rubber band, if we talk about the normal strain, change in the length or the width or the thickness of the rubber band, and that is all about the normal strain, epsilon. The other type of strain that we call shear strain, so the deformation is not always about the changes in length, but it can be any distortion, angular distortion. For example, here, if you see this plastic member horizontal, if I apply a load, twist, and you see that the line is no horizontal, it twists, the angle it distorts. So 0, it distorts. In this case, it basically is the angular distortion, and this is one form of deformation, and that for that form of deformation we use shear stress and shear strain to represent it. So as you watch that demonstration, we know the two types of deformation, the change in length, width, and thickness of the body, and the other type of deformation is the angular distortion, and that go with the shear strain that I'm going to take here. So let's put a diagram to show what is that about. So if we call it the x and y direction, and we have in 2D we have x and y axis, and if we have the original bodies, let's see a block, square blocks, and for angular distortion, as we apply a load P here, if we apply the load P, go to that direction, then that square block may distort if we apply the load P. And as you can see, that angular distortion, original square, but the angle there is not square anymore. So that change in that angle here, if we extend that line down, here, that angle, we call that here gamma 2. That angle here called gamma 1, or you can change gamma 1 to gamma 2 and gamma 2 to gamma 1. So for that, the shear strain gamma, in that case, we have gamma, and it both x and y direction. So normally we call it shear strain xy in x and y axis. It equal to the total of gamma 1 and gamma 2, gamma 1 plus gamma 2, and that basically we call that here shear strain. So measured by the angle of the distortion after we apply the load P in there. So you can see we need to have some sign convention, positive, negative, just like the force, right? So let's talk about the sign convention. For shear strain. So when the theta decrease, then it will be positive for gamma. So for example, in this case, the case that we demonstrate there, so it will be positive if theta, the angle in there, decreases. And of course opposite is negative shear strain if theta is increases. Just like you apply the load P in opposite direction, that change that angle increase that angle from 0 to there. So from that we have the unit at the angles. So it's not about the degree, it measures in radians, unit radians. So bottom line, the normal strain measured inch over inch, millimeter over millimeter. Shear strain, gamma, measured in radians. So similar to after you study normal strains, we have the normal stress and normal strain curve, and that is unique for one material. It's the same for apply for shear stress and shear strain curve. So let me draw that out here. So it will have shear stress, shear strain curve. Similar to normal stress, normal strain curve, we have shear stress and shear strain curve. So in 2D, two direction, so you have put here tau, which is the shear stress, KSI, and we have gamma in radians. So the behavior, it also have elastic and plastic region, and it will be something like linear portion, and then it go to plastic region. So similar to the normal stress, normal strain curve, they have two regions. The first one here is elastic. Let's move up a little bit. Elastic. And the rest, it will be plastic or inelastic, plastic region. So as you can see that the curve is similar to the curve for normal stress, normal strain curve in there. And if we go 1 in epsilon, we have E similar to that curve in the linear portion. We can do exactly the same. And if we go to the shear strain horizontally 1, go up, it will be constant in that linear portion, and that we call it chi. So what is chi? In here we can see that chi equal to the ratio between the vertical, horizontal, so tau shear stress divided by shear strain gamma. So let's box that definition. Same as E, Young modulus, sigma over epsilon. Now chi, tau over gamma. And that chi, we call it modulus of rigidity. Chi, it will be modulus of rigidity. Or because it's about shear, right? Shear stress, shear strain. So it also called that a shear modulus. Shear modulus. Shear modulus. So bottom line, we have a few material properties, material constant that I want to summarize before we conclude for this lesson. So let's talk about some material property that we introduced today. Material constants and their relationship. So we have the first one, as you can see, E is the modulus of elasticity, modulus or Young modulus of elasticity. And then chi is modulus of rigidity and Poisson ratio nu here Poisson ratio. And believe it or not, they have a relationship. They have a relationship. And that relationship I'm going to write out in here. Chi for the modulus of elasticity is equal to E and inelastic region, and you can see 2, 1 plus Poisson ratio nu. So that equation box there. So if you know two material constant, either E nu, we find out chi. If we know chi E, you find out nu, or we know chi and nu, you find out E. So that's for the material. And for all of that, you can go back to the reference that we have. You have modulus of rigidity, for example, very first line, structural steel, ASTM A36. Modulus of rigidity is 11.2, 10 power 6 psi. Modulus of elasticity, 29, 10 power 6 psi. So from those two, you can be able to find out the Poisson ratio for the steel, and similar apply for cast iron, aluminum, copper, etc. And if you cannot find that, it go to the reference data card page number 4. We have that for steel, aluminum, cast iron, and wood for modulus of elasticity, modulus of rigidity, chi, Poisson ratio, and coefficient of thermal expansion alpha that we are going to talk next week. So with that, we done for today's lesson.